This slide introduces Svante Arrhenius, the brilliant polymath celebrated for unlocking the arithmetic of our universe. Renowned as a founding father of physical chemistry, Arrhenius bridges the worlds of physics and chemistry with fundamental formulas like the ones faded into the background. Yet his genius extended far beyond the laboratory. He was a visionary who first predicted the greenhouse effect, anticipating modern climate science by generations. From quantifying the complex mechanisms of the cosmos to calculating global temperature shifts, this presentation explores how Arrhenius's mathematical precision reshaped our understanding of the Earth and the stars. This slide maps out the expansive scientific legacy of Svante Arrhenius across 4 groundbreaking quadrants. In physical chemistry, we see his foundation of electrolytic dissociation and chemical kinetics, which earned him the 1903 Nobel Prize. Moving to atmospheric physics, his landmark 1896 greenhouse model became the first to successfully quantify CO2's impact on global temperatures. Looking outward to cosmic physics, Arrhenius proposed radiopanspermia, the visionary idea that life spreads through space via spores propelled by stellar light. Finally, in immunochemistry, he applied mathematical physical chemistry to biological kinetics, modeling complex toxin-antitoxin interactions. Together, these quadrants showcase a brilliant mind that seamlessly bridged the molecular and the cosmic. This slide illustrates a dramatic arc from institutional rejection to ultimate scientific triumph. On the left, we explore 1884, the crisis of orthodoxy. Arrhenius's radical 150-page doctoral thesis on electrolytic conductivity was granted a near-failing, 4th class, grade by his conservative professors. Traditionalists vehemently rejected his core conflict, the notion that salts could spontaneously split into charged particles without an electric current. On the right, we witness 1903. The Nobel vindication. Championed abroad by European physical chemists in Riga, Würzburg, and Amsterdam, his revolutionary ideas persevered. In a stunning resolution 19 years after his academic dismissal, the exact same, flawed, thesis earned Arrhenius Sweden's very first Nobel Prize in chemistry. This slide illustrates a foundational paradigm shift in chemistry, electrolytic dissociation. On the left, the Faraday orthodoxy, pre-1884, represents the prevailing historical belief. Scientists assumed that stable molecules like sodium chloride required an external force, a literal electric spark, to violently tear them apart into active ions. On the right, the Arrhenius reality, 1884, reveals his revolutionary discovery. Arrhenius proved that no electrical intervention is necessary. Instead, salts automatically dissociate into active ions, such as sodium and chlorine, the very moment they hit water. By identifying these spontaneous ions as the fundamental carriers of chemical activity, Arrhenius forever changed our understanding of chemical reactions and solutions. This slide deconstructs the geometry of chemical speed, 1889, through the famous Arrhenius equation. 4 critical components govern this relationship. First, K is the speed limit, the rate constant tracking how fast a reaction actually occurs. Second, A represents the collision factor, or the frequency of molecules colliding with the correct spatial orientation. Third, EA defines the energy barrier, the minimum activation energy required to trigger the chemical transformation. Finally, T acts as the heat engine, representing absolute temperature. By linking these variables, Arrhenius provided the world's first quantitative proof of why even a tiny increase in heat exponentially accelerates chemical reactions. This slide visualizes the temperature effect using a reaction coordinate diagram, mapping potential energy against the progress of a chemical reaction. To transform reactants into products, molecules must climb an energetic hill, reaching a peak known as the transition state. The height of this hill represents the activation energy, EA. Arrhenius realized that molecules require a minimum threshold of kinetic energy to clear the hill. Crucially, his insight reveals that heating a system does not actually lower the barrier. Instead, adding thermal energy increases the fraction of molecules moving fast enough to successfully scale the peak, thereby exponentially driving the reaction forward. This slide outlines modeling the global thermostat, 1896, Arrhenius's pioneering work to solve the riddle of the ice ages. He discovered a complex feedback loop. First, volcanoes and industrial coal emit CO2 as an initial forcing. Next, this CO2 traps infrared heat radiating from the Earth, causing global atmospheric temperatures to rise. Crucially, Arrhenius noted that warmer air holds exponentially more water vapor. Because water vapor is also a potent greenhouse gas, it amplifies the initial heat trapping, feeding directly back into the warming cycle. By establishing this relationship, Arrhenius identified CO2 as the primary control knob governing the water vapor cycle, setting our planet's long-term equilibrium temperature. This slide highlights the 1896 climate projections, comparing Arrhenius's manual formulations with modern data. For the first scenario, having atmospheric CO2, Arrhenius calculated a drop of -4C to -5C, predicting it as the trigger for a new ice age, a mechanism the modern IPCC consensus validates as highly accurate for glacial cycles. For doubling atmospheric CO2, he projected a +5C to +6C global temperature rise, remarkably close to modern estimates of +3C to +4.5C. Astonishingly, Arrhenius spent months computing infrared absorption across various latitudes and seasons entirely by hand. Without computers, his brilliant arithmetic yielded predictions that remain remarkably aligned with today's advanced supercomputer models. This slide explores radiopanspermia, the universal spread of life, highlighting Arrhenius's fascinating venture into cosmic biology. Under the postulate, we learn that in his 1908 book Worlds in the Making, Arrhenius rejected spontaneous generation, instead arguing that life is eternal and ubiquitous throughout the cosmos. The mechanism shows his detailed mathematical calculations proving that microscopic bacterial spores could be physically propelled through interstellar space, driven purely by the radiation pressure of stellar light. Finally, the legacy notes that while the extreme lethality of cosmic radiation makes this exact mechanism unlikely today, Arrhenius's bold hypothesis laid the vital conceptual groundwork for modern astrobiology, expanding our search for life among the stars. This slide chronicles the birth of immunochemistry, 1902, where Arrhenius shattered long-standing scientific silos. Under collapsing boundaries, we learn he rejected the contemporary belief that biological interactions between toxins and antitoxins were driven by mysterious, vital forces. Instead, looking at universal laws, Arrhenius applied kinetic rate curves to prove that the human immune system obeys the exact same laws of physical chemistry as simple salts reacting in a glass test tube. Finally, his impact culminated in the 1907 book Immunochemistry. Despite fierce opposition from traditional physiologists such as Paul Ehrlich, this work established a rigorous, quantitative foundation for immunology, thereby permanently cementing mathematics and physical chemistry at the heart of biological science. This slide details Arrhenius's role as the power broker of Swedish science, mapping out his immense institutional and societal control. At the top, his permanent power base is solidified as the director of the Nobel Institute for Physical Chemistry, 1905, a prestigious position created explicitly for him. Branching downward, Arrhenius wielded massive authority within the Nobel Committee, exercising immense influence over early physics and chemistry prizes to internationalize Swedish science while actively gatekeeping rivals like Mendeleev. Concurrently, his influence shaped industrial electrification, where he chaired royal commissions on hydroelectric power and drove the electrification of the Swedish railway system. Through these interconnected pillars, Arrhenius masterfully merged academic physics with national infrastructure and global recognition. This slide confronts the limits of the ledger, controversies and blind spots, examining the flaws of Arrhenius's calculations when applied to complex systems. On the left, his climate optimism shows a profound blind spot. Arrhenius believed human-induced global warming would be purely beneficial, fostering better climates for agriculture. This localized, Nordic-centric perspective completely failed to foresee the catastrophic ecological and social disruptions of rapid climate change. On the right, we confront his involvement with eugenics and racial hygiene. As a 1909 board member of the Swedish Society for Racial Hygiene, Arrhenius attempted to apply rigid mathematical arithmetic to human biology, tragically lending his immense scientific prestige to a deeply flawed and damaging pseudoscience. This slide evaluates Arrhenius through a modern lens, offering a definitive report card on his lasting scientific legacy. First, his theory of electrolytic dissociation remains correct, though it required later Debye-Huckel modifications for strong electrolytes, cementing him as the founder of physical chemistry. Second, his concept of activation energy is universally accepted as the absolute foundation of chemical kinetics. Third, his work on the greenhouse effect is completely proven. While he underestimated the timeframe, he remains the father of modern climate modeling. Lastly, while radiopanspermia was largely discarded due to the lethal radiation of space, it successfully sparked academic astrobiology. Arrhenius's core postulates endure, standing as a testament to an extraordinary mind that shaped modern science. This final slide brings us to the final legacy, a powerful conclusion to our journey through the life of a visionary. It summarizes how Svante Arrhenius fundamentally transformed chemistry, elevating it from a purely observational science into a rigorous, mathematical discipline. By boldly refusing to respect the traditional borders separating chemistry, physics, biology, and astrophysics, he laid the vital conceptual groundwork for our modern scientific world. He leaves behind an enduring reputation as the ultimate polymath, the man who found the true arithmetic of the universe.